Sorting is one of those Python topics that feels easy until the interview problem adds one extra condition. In this video, we will solve 15 real sorting challenges with clear inputs, outputs, and explanations. By the end, you will know how to choose the right sorting strategy fast. We start with the core sorting tools you will use in almost every Python interview. These examples focus on clear inputs, clear outputs, and the difference between creating a sorted copy and changing data in place. When a report needs numbers from lowest to highest, Python already gives us the cleanest tool. Let's write a small function that accepts a list of integers, returns a sorted copy, and then we run the script to compare the original list with the result. Let's break down the result. Sorted returns a brand new list, so the values become 1, 2, 3, 5, but the original input is still 5, 1, 3, 2. That matters when other parts of your program still depend on the original order. The best practice here is to use sorted when you want a sorted copy. It keeps your function predictable because callers do not lose the original order by surprise. Now try a quick variation yourself. Replace the input with 10, -2, 7, and 0. Then predict which number appears first before you run it. Leaderboards usually show the biggest score first, not last. Let's write a function that receives player scores, sorts them with reverse set to true, and now we run it to see the ranking. Let's look at why the output starts with 450. Python still sorts the numbers normally, but reverse true asks for the final order to be largest to smallest, so the leaderboard reads like a real ranking. The best practice is to use reverse true for simple descending sorts. It is direct, readable, and avoids writing extra logic that Python already handles well. For practice, add a score of 500 to the input. Before running it, predict where that score should appear in the output. Menus, usernames, and product lists are easier to scan when they are alphabetical. Let's sort a small list of lowercase product names. Then run the script and inspect the output. Let's break down the ordering. With lowercase words, Python compares the text from left to right, so apple comes before banana, and banana comes before cherry. No key function is needed for this simple case. The best practice is to keep the default sort when your text data uses consistent casing. It makes the code short and keeps the sorting rule obvious. Now try adding apricot to the list. Think about whether it should appear before or after apple, then run the code and compare your prediction. Now we move beyond default order. A key function lets us tell Python what value to compare while keeping the original items in the list. Customer names often arrive with mixed capitalization, but the UI still needs a natural alphabetical order. Let's sort by a lowercase version of each name, keep the original spelling, and now run the script to see the result. Let's unpack the key function. Python calls str lower for comparison only, so Bob is compared like Bob and Ann is compared like Ann. The displayed values still keep their original capitalization. The best practice is to normalize inside the key function. This gives you the ordering you want while preserving the data exactly as the user entered it. For practice, add Aaron and Zoe to the list. Check whether a lowercase name and an uppercase name still land in the correct alphabetical positions. Search suggestions can be easier to read when shorter options appear first. Let's sort these words by their length with the len function, then run the script and check the order. Let's break down the result. Go has 2 letters, Java has 4, Python has 6, and JavaScript has 10. The key function tells Python to sort by those numbers instead of sorting the words alphabetically. The best practice is to use a key function whenever the rule depends on a derived value. Here, the derived value is length, but the same pattern works for dates, prices, scores, and object fields. Now try adding Rust and TypeScript. Notice what happens when 2 words have the same length, because Python keeps their original relative order. In this section, we sort data that is more realistic than a plain list of numbers. The key idea is choosing the exact field Python should compare. Here is a common interview-style task. Each product is stored as a tuple with a name and a price. We want the cheapest product first, so let's use a key function that points to the second tuple value. Now we run the script and check the order. Let's break down why this works. The lambda runs once for each product and returns only the price. Python compares those prices, but the result still contains the original full tuples. The best practice here is to keep the selected field obvious. For short examples, a lambda is fine, and in production code, item getter can make tuple position sorting even clearer. Now try a small variation yourself. Sort the same product list from highest price to lowest price, and keep the tuple records exactly as they are. In real applications, records are often dictionaries instead of tuples. Here we have user profiles, and the task is to order them from youngest to oldest. We point the sorting key at the age field, then run the script and inspect the full records. Let's break down the result. Leo has the smallest age value, then Nora, then Maya. The sort key decides the order, but each dictionary stays complete in the output. The best practice is to keep dictionary keys explicit and consistent. If one record is missing age, this key function will raise a key error, so validate incoming data before sorting. For practice, add another user dictionary and sort from oldest to youngest. The key stays the same, but the direction changes. Now we move from one sorting rule to multiple rules. This is where tuple keys become very useful in interviews and production code. Sometimes one field is not enough. In this candidate list, the main rule is higher score first, and tied scores should be ordered by name. We return a tuple from the key function, then run the script to see both rules applied. Let's break down the tuple key. Negative score turns a descending numeric sort into a normal ascending sort. When Adam and Mia both have 95, Python moves to the second value and compares their names alphabetically. The best practice is to make tie-breaking deterministic. If two records can share the main value, add a second key so the output is stable and predictable. For practice, add an experience field, sort by score descending, then experience descending, and finally name ascending. The last section handles values that look sortable but are not safe as plain strings. We will convert them into comparison-friendly values first. Date strings can trick you because alphabetical order is not always calendar order. These API-style events use month, day, and year, so we parse each date inside the key function. Now we run it and check that the events are chronological. Let's break down why this is safer. The visible date stays as a string in the record, but the value used for comparison is a date-time object. That gives Python the real calendar order. The best practice is to parse dates before sorting when the format is not ISO style. This avoids bugs where text order and time order accidentally disagree. For practice, add one event from the previous year. If your key function is correct, that event should move to the beginning of the list. Version numbers are another place where plain string sorting gives the wrong idea. The string 1.den should come after 1.3 numerically, so we split each version into integer parts. Now we run the script and check the corrected order. Let's break down the comparison. As text, 1.10 can look smaller than 1.3 because characters are compared one by one. As numbers, 10 is greater than 3, so 1.10 belongs later. The best practice is to avoid plain string sorting for values that contain numbers with meaning. Convert the parts to integers first or use a dedicated version parser when versions include labels like alpha or beta. For practice, add patch versions like 1.0.5 and 1.0.1. The same key function should still compare each numeric component correctly. Now we move from basic lists to real application data. Sorting objects is common in tools that work with users, employees, products, orders, and records. In real projects, we often sort objects instead of plain numbers. Here the task is to sort employee instances by salary, so I will create a small class, build a few employees, and pass a key function to sort it. Now we run the script and check that the lowest salary appears first. Let's break down why this works. Python does not need to compare whole employee objects directly. The key function extracts one sortable value from each object, and sorted uses those salary numbers to build the final order. Now we show the best practice for this pattern. Prefer a key function when the sort order is local to one task, like salary here. Only add comparison methods to the class when the object has one natural order across the whole code base. For a quick variation, try sorting these same employees by name, change the key to employee.name, run it again, and confirm the output is alphabetical. Next, we use sorting as a selection tool. This is useful when the interview question asks for the biggest, smallest, newest, or highest scoring items. Imagine we have monthly sales numbers and need the top 3 results. For a clean interview solution, I will sort the values in descending order and then slice the first K items. Now we run it and look for the 3 highest numbers. Let's break down the result. The sorted call creates a descending copy, so the largest values move to the front. The slice then keeps only the first three elements, which are 98, 91, and 87. Now we show the best practice. Sorting is a great first solution when the list is small or the code needs to be very readable. When the dataset is huge and k is small, mention ECPAN largest because it can avoid sorting everything. For practice, flip the problem. Write a function called bottom k smallest that returns the k lowest values in ascending order. This checks whether you understand both the sort direction and the slice. Now we reach two classic interview patterns. These problems are less about calling sorted and more about choosing the right algorithm for the shape of the input. When two data streams are already sorted, sorting again wastes useful information. Here I will use two pointers, one for each list, and always append the smaller current value. Now we run the script and confirm the merged list is sorted. Let's break down why this is efficient. Each pointer only moves forward, so every value is visited once. That gives us linear time instead of paying for a full sort after combining the lists. Now we show the best practice for interview reasoning. If the input arrays are already sorted, say that out loud and use that fact. The two-pointer merge is faster and communicates that you notice the important constraint. For practice, try uneven list sizes, merge one short list with one longer list, and make sure the extend calls correctly append the remaining tail. Here, the list contains only 0, 1, and 2, like 3 status categories. I will sort it in place using low, mid, and high pointers, so we do not create another list. Now we run it and watch the same list become sorted. Let's break down the pointer roles. Low is the next position for a 0. High is the next position for a 2, and mid scans the unknown part. When mid sees a 1, it is already in the middle group, so we just move forward. Now we show the best practice. When the input domain is tiny and known, use a specialized linear algorithm instead of reaching for a full comparison sort. This is exactly the kind of optimization interviewers expect you to recognize. For practice, run this with a different color order and trace the pointer movement by hand. Pay special attention to the case where we swap with high, because mid does not move immediately there. The final problem is about using the structure of the data. When an array is almost sorted, a heap can be more efficient than a full general sort. Sometimes event data arrives almost in order, but a few items are slightly late. Since every value is at most k positions away from its final place, I will keep only k+1 candidates in a min heap. Now we run the code and confirm the result becomes fully sorted. Let's break down the heap idea. If an element can be at most 2 positions away, the smallest remaining value must be inside the next 3 candidates. The heap gives us that smallest candidate quickly, then we slide the window forward. Now we show the best practice. Use this heap approach when the array is truly nearly sorted and k is much smaller than the full input size. If k is close to n, a normal sort is usually simpler and just as reasonable. For the final practice, test a longer nearly sorted array with k equal to 3. Compare the heap result with Python's sorted result to prove your function is correct. Now you have 15 practical sorting patterns you can reuse in interviews in real projects. If this helped, like the video, subscribe to Dev Level Up, and write in the comments which Python topic you want next.